Hello, welcome. This is Discrete Mathematics, and today we are talking about section 3.5, Matrices of Relations. We are going to use a matrix of relation to represent a relation R from X to Y. The way that we're going to do that is we're going to label the rows with elements of X and the columns with elements of Y. So here's your quick, very brief matrix reviews. This is a matrix. Let's see, I'll just write one down here. Okay, so this one has 4 columns and 3 rows. And so we would say that the size is the rows times the columns, which is a 3 by 4 matrix. So when we're doing this, we're labeling the rows with elements of X and the columns with elements of Y. And then anytime we have that element in the set, we would put a 1 there. Otherwise, we put a 0 in. So let's look at the matrix of relation for R, where R is 1B, 1D, 2C, 3C, 3B, 4A, where X goes from 1 to 4 and Y goes from A to D. So my matrix, which I'm going to call matrix A, is going to look like this. So on here, I'm going to put X, which is 1, 2, 3, 4. And then up here, I'm going to put Y, which is A, B, C, D. So this is going to be a 4 by 4 matrix. There'll be 16 rows. There are 16 entries in this matrix. So here, 1B is going to be 1B right here. So I'm going to put a 1 right here. 1D, I'm going to put a 1 right here. 1D. And then there's no other things in row 1. So these are going to get zeros. And then 2C is going to be here, and then no other 2s. So I'm going to add zeros. 3C and 3B, and then zeros. And then 4 is A, and then zeros. So there are 1, 2, 3, 4, 5, 6 elements in my matrix, and 1, 2, 3, 4, 5, 6 ones in my matrix, and everything else is a 0. There's 6 elements in my set. Did I say that right? And then 6 elements in my matrix. All right, let's do another one. Find the matrix of the relation R, where R is AA, BA, CD, DD, CB, and BC on A, B, C, D. So this is for X and Y. So here's going to be A. We'll have A, B, C, D, and A, B, C, D. Let's see, AA. And then are there any other A's? No. So I'm going to do zeros. And then BA. And then BC. And then CD and CB. And then DD. So here is my matrix for this one. Matrix of the relation. If you need a refresher on matrix algebra, really the only matrix algebra that we're going to do in this section is multiplication. We're not really going to do a lot with like multiplying it by a scalar or adding matrices together, but we are going to do matrix multiplication. You can do matrix multiplication on A and B if the number of columns in this first matrix is equal to the number of rows in your second matrix. That's the only way that you can do matrix multiplication. So we'll take a look at an example of matrix multiplication here. I think it's probably best. This is kind of the formal definition. I think it's probably best if we just look at an example. So in example 3, I've got 2 matrices, A and C. I want to know what is AC and what is CA. So if we look at AC, that AC is a 2 by 3 matrix and C is a 2 by 2 matrix. So I'm looking for 2 by 3 times a 2 by 2 matrix. And I actually can't do this, and that's because these two elements, or these two numbers, have to be the same in order to do this. And I can't do that, because what I'm going to do is I'm going to take this column and put it on top of this row, and it's not long enough. It needs another element down here. So this one is not going to work. So since we can't do this, it's called undefined. But we can do CA. CA is a 2 by 2 matrix times a 2 by 3 matrix. So I actually can do it because these two numbers are the same, and my resulting matrix is going to be a 2 by 3. So let's write out what this is going to be. C is 3, -2, -1, and 6. And A is 3, 0, -1, 2, -7, 5. So what I'm going to do is I'm going to put this column onto that row. So I'm going to do 3 and 3 and -2 and 2. So here's my resulting matrix. 3 times 3 plus -2 times 2. That's going to be the first entry in this matrix. And then I'm going to do the second column, still on this first row. I'm going to have 3 times 0 plus -2 times -7. And then third one, I'm going to have 3 times -1 plus -2 times 5. So now I'm going to erase all of these, erase that, and now I'm going to put everything on the second row, and that's going to be my bottom row of my resulting matrix. So 3, -1 times 3 plus 6 times 2, -1 times 0 plus 6 times -7, and -1 times -1 plus 6 times 5. So you can use a calculator or use your mental math. This is going to be 9 and -4 is 5. This is going to be 0 and 14. It's going to be -3 and -10 is -13. You end up doing all the entries. This is 9 and -42 and 30 and 31. And then this size is a 2 by 3. So this is matrix multiplication, meant to be a review. There are lots of resources available for matrix algebra. If you need any help with that, please let me know and I can provide something for you. One thing to note is that, maybe I'll make my note here in green, and that is that matrix multiplication is not commutative. And that is to say that AC is not the same thing as CA. I couldn't even do AC, but I could do CA. So my matrix multiplication is not commutative. Okay, so that's your review. Let's take a look at our properties, reflexive, symmetric, and transitive, and how those look like with matrices. So relation matrices contain ones and zeros. The matrices contain 1 or 0 as all of their entries. So a reflexive matrix, let's just take a look at what one might look like. Let's say that X is A, B, and C. And in order to be reflexive, R needs to contain all the loops. It needs to contain AA, BB, and CC. And it can contain other stuff too, but it needs to have those 3 elements for it to be reflexive. So if this is what my matrix looks like, A, B, C, A, B, C, it needs to have AA, BB, and CC. And then the rest of these entries can be 1s or 0s. It doesn't really matter if for the reflexive part of it. So this is what a reflexive matrix would need to look like. So as we're analyzing that pattern, what I'm noticing is that there's 1s along the diagonal. So therefore, diagonal entries must be 1. So we saw a version of this property when we looked at the digraphs, and that was that we had to have all the loops in the digraph. So here's the matrix version of that. All of the entries along the diagonal must be a 1, and then the other entries can be, whatever. Okay, that's reflexive. Symmetric, if R is symmetric, what does that matrix look like? Let's say that X is the same thing, A, B, and C. And to be reflexive, if AB is in R, then BA must be in R. So let's just look at A, B, and C, A, B, and C. So if I have A, B in R, that's this one, then BA has to be in R. That's this one. So the rest of these can kind of be whatever. So as I'm looking at what this would look like, if AC was in R, so maybe I'll do that as another one, then CA would have to be in R. That would be this one down here. So if I look at my diagonal again, this is the diagonal. If we would fold this matrix in half along the diagonal, it would match up. So it's a mirror image about the diagonal. Matrix is a mirror image about the diagonal. So another way of saying that, if we go back to that matrix notation, Aij is equal to Aji. So maybe I'll do another symmetric matrix, just another example of a matrix that's symmetric would be something like 1, 2, 0, 2, 3, -4, and then this has to be -4. Oh, sorry, this has to be 0. And then -4, and then, I don't know, 5. So as I go along this diagonal, I'm seeing that 2 is matching up with 2, 0 is matching up with 0, and -4 is matching up with -4. So this is symmetry about the diagonal is a symmetric matrix. Nice way to remember that. Last one, what does a transitive matrix look like? And this is one that we're going to have to do quite a bit more work for. This is where that multiplication that we looked at earlier comes in. So here we have a theorem. Let R1 be a relation from X to Y, and let R2 be a relation from Y to Z. And you can choose the orderings of X, Y, and Z. The orderings help you determine where along the matrix you're going to put things. Let A1 be the matrix of R1, A2 be the matrix of R2 with respect to those orderings that you picked. The matrix of the relation R2 composed with R1 is obtained by replacing each non-zero term in the matrix product A1 times A2 by 1. So in order to use this theorem, we'll have to write down what's A1 and A2. Those are the matrices of the relation. We've been practicing that. We'll need to find the product A1 times A2. We also practice that. And then whatever that product is, anytime there's not something that's not 0, we're going to put a 1, because our matrix, our relation matrices can only have 0 or 1. So if we see like a 2, for example, which, spoiler alert, we will, we'll replace that with a 1. And then we'll take a look at what that looks like. Okay, example 3. Consider R, which is AA, BB, CC, DD, BC, and CB. What is the matrix of relation A? What is the matrix of the relation A squared? And find the matrix of the relation A composed with A. And it as a matrix, and then I also want to write the set of ordered pairs. And I want to know, is that relation transitive? So first up, maybe I'll label some of these. We'll say this is A, what is B, and then this will be C. And this will be D, and this will be E. Okay, so here we are with A. I want to write down the matrix of relation A. So I didn't really specify orderings here, but let's just assume the orderings are A, B, C, D. A, B, C, D. A, B, C, D. So we're seeing A, B, B, C, C, and D, D. So that's all along the diagonal. So this one is reflexive. And then I'm seeing B, C, and CB. So that's this one, and then all the rest of these are 0. Okay. So we're actually also seeing some symmetry. So this one is symmetric and reflexive. That's so cool. We'll see if it's transitive. Let's look at, in part B, what is A squared? That's going to be A times A. So that's 1, 0, 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1. I guess I drew my thing too big. And then another one of these. I like to write out what the matrices are. That way I can, oops. When I do the product, that way I can more easily do my mentally, like, oh shoot. I can do my mental, I'm putting this on here. So this is going to be 1, and then a bunch of plus a bunch of zeros. And then I'm coming down here. This is going to be 0, 0, 0, 0. Okay. And then same thing. And then 0, 0, 0, 0. A lot of zeros in this one. Okay, so now I'm looking at this one. So first entry 0 and then a bunch of zeros. Next entry 0 and then 1 plus another 1 is 2. And then another 0. Or then 1 plus another 1 is 2, and then another 0. Next one is actually going to be exactly the same. 0, 2, 2, 0. And then the last one is zeros, and then zeros, and then zeros, and then 0, 0, 0, and then a 1. These two are going to end up together with the 1. Okay, so that is a squared. A couple 1s, a bunch of 2s there in the middle, and then zeros. Now I want to figure out part C, which is find the matrix of relation A composed with A. So I have A squared. So I'm going to say that B is going to be A composed with A. And that's going to be this matrix, but change all those 2's to 1's and leave everything else alone. So that's 1, 0, 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1. Does that look familiar? That is equal to A. So that means that yes, this relation is transitive. So that is how you check a transitive relationship. You look at A squared, and then change all of the non-zero elements to 1's. And then if that's the same thing as A, then it's transitive. So actually this is a transitive. That was part E. So sorry, I'm jumping ahead. I skipped part D. Part D is to write all the ordered pairs of B, of this A composed with A. And the set of ordered pairs is equal to R, because this matrix is the same as A. And the set of all the ordered pairs of A was R. That's what we started with. So my set of ordered pairs here is the same thing as R, that set of ordered pairs. So I mentioned this a little bit earlier, but as an aside, we noticed that A was symmetric, and it is reflexive, and we just showed that it is transitive. So what does that mean? That R is an equivalence relation. Isn't that exciting? I'm excited. Okay, let's move along to example 4. This is the last one for today. Consider R1, which is 1x, 1y, 2x, and 3x, and R2 is xb, yb, ya, yc. The orderings of x and y are 1, 2, 3, xy, and abc. So kind of what you would expect. Find the matrix of relations of R1 and R2. Find the matrix product, R1 times R2. Find the matrix of the relation R2 composed with R1, and express the relation as a set of ordered pairs. So we're doing a lot of the same things we did in the last one. Let's see, I want to find A1, which is, okay, so let's see. These first ones are the elements of the column, so that's 1, 2, and 3. And then for are the elements of the rows. And then for my columns, I'm doing x and y. So I've got 1x, 1y, 2x, and 3x. So zeros there. That's A1. And A2 is, let's see, the x's and y's this time are the rows, and the columns are A, B, and C. So I've got xb and yb and ya and yc. No xa and no xc. All right, in B, we are looking for A1 times A2. A1 is a 3 by 2 matrix. A2 is a 2 by 3 matrix. So we can do this, and our result is going to be a 3 by 3 matrix. So I'm going to do this one with this. So that is 0 and 1. And then this one with this, 1 plus 1 is 2. This one with this, 0 and 1 is 1. Going on to the second row. 0 and 0, 1 and 0. And third row, 0 and 1 and 0. All right, and so then in part C, we are looking at matrix B, which is the matrix of the relation R2 composed with R1. Maybe I'll just call it that. And that is going to be this matrix, but I'm going to replace that 2 with a 1. 1, 1, 1, 0, 1, 0, and 0, 1, 0. And I'm going to relabel, this is A, B, and C, and this is 1, 2, and 3. And I want to do that because here in part D, I'm going to write all the ordered pairs. So the ordered pairs are 1A, 1B, and 1C. And then I've got, let's see, 2B and 3B. And that's my set of ordered pairs. I'm not checking for transitive relation here because that's for like one set where you do it with itself. Like here we did A squared, A with itself. So that's not really an option for this one. So no transitive here. That's the end of this one. And so I will see you next time.